Hello, everyone. My name is Yang, and I'm going to talk about our work that is Code-DKT, published in EDM 2022 today with you. Thanks for coming to my presentation. So let me get started. So the key contribution of our work is that we incorporated some code features into the original deep knowledge tracing model, which you should already familiar about for some of you, right? So we have the original Code-DKT that has the input as the students' previous scores when they practice some like skills or questions, such as like this. You want to make the predictions whether they can make it correct on their next submissions on different problems. And our contribution is that we incorporated the code features in. We added program-specific features to DKT and improved the accuracy or AUC scores by at least 3.07% in our experiments. And we also investigated like when and how Code-DKT improves the performance of DKT. And here are some related work here, right? We have the domain general knowledge tracing, we have the Bayesian knowledge tracing, we have DKT, the base models, and we have the transformer-based models such as like SAKT, SAND, etc. And those ones, the key innovation there is about the structure of the neural network. And here we also want to address the issue in CS education because it has code as submissions. And in CS education, it is more complex in a lot of cases because sometimes students doesn't practice single skills in one submission. In a submission about if condition, you don't only just practice if, you maybe will also practice the logics, the other things like variables, right? So it is not a simple skill. It is very interconnected skills. Then we have some previous work about student modeling in CS education. We model students' code to see what they know, what they don't know. And we also just model students' misconceptions, detect them, and try to see whether we can make the feedback to them. We also have some previous work about deep code learning. Originally, people used the natural language methods to analyze the code, such as like word2vec, sorry. And recently, we introduced like program-specific models, such as Code-2vec. And now we use Code-2vec as an example usage in the educational domain to see whether that integration works for this domain. Specifically for Code-2vec, we use AST, abstract the syntax tree, to serve as the input, right? So assume that we have a code like this. We define a method, and then we have the tree. The leaf node, the root node of the tree is the method, and then it has an input and maybe some like body of the program, right? So then you have a left branch, which is the input, and the right branch of this method is a body. First line of this body is about do something with this input, and the second line is about like return the string that is the value. So if we want to use vectors in the machine learning algorithms, we want to represent this tree into some numbers. How we do that? We use leaf-to-leaf path to do this. For example, we have this path. We also can extract this path in this AST. And we can represent the starting node, the ending node as some numbers, like the embeddings, right? And also we can also embed the whole trace, the whole path as the numbers. Specifically, we did something like this. This is called DKT structure. The input is a path, and then we use an embedding layer to embed them into some numbers and concatenate them together with the score information to select the weight of each of the features using an attention mechanism. And this score information is concatenated because it can also help to determine which of the path is more important in making the predictions. And then it is concatenated finally together as a weighted sum And this is the code vector, right? You use this code vector to be concatenated with the correctness vector originally used in the DKT to pass through the final LSTM layer to make the predictions. So this is basically how Code-DKT works. It's a concatenation of the code features and the original used correctness features for the DKT model. We did some experiments here. We used the code workout dataset from Virginia Tech that is recorded in spring 2019 in the CS1 class. It is a Java class, and every student, every submissions, they have 10 to 20 lines of code. And we have 410 students. We have like 50 problems and 5 assignments for the data sets. Each assignment will have 10 problems specifically practicing some set of like skills. And overall, we have 23.68% of attempts that they are correct. We have the trend testing speed as 4 and 1. And we have 100 times running for hyperparameter tuning because we want to make the hyperparameters we selected as stable. So we have the embedding size selected as this, and we max the 50 submissions for each of the assignments because we don't want to dig too deep into like why students fail 200 times, right? So yeah, so the experiments are done with the traces within one assignment at a time because different assignments try to have different emphasis on the skills. We compare with some baseline models. We compare with deep knowledge tracing. We compare with the Bayesian knowledge tracing. We also compare with some basic NLP approaches, such as like TF-IDF to extract the code features. We also compare with the expert features, such as like experts try to use some rules to extract the features from the code and then concatenate with the DKT. We compare with these two models as well. The result here is the performance, right? So we see like all the 5 assignments, Code-DKT performs better than DKT, at least by 3.07 on the AOC scores. And we can also see like, well, Code-DKT performs better, even better on the first attempts. When students change to another problem, it is even better than DKT, right? And for the other simple like features, such as like NLP features, DF-IDF, TF-IDF, or the rule-based features from experts, they just simply doesn't work, which shows like structural information extracted are more important. And we can also say like, well, DKT is much better than BKT in this situation. So we further decompose this result, we can see on some of the problems, Code-DKT, they are better on 6/9. I think this is a good percentage, right? On problem 13, it is like way better than DKT. However, on 236, it is like worse than DKT. But why? Then we say like, okay, in some problems, they share the similar concepts. Code-DKT tend to perform better on these problems on 5 of the 6 problems that share the similar concepts of nested if, which means that, well, when they share the similar concepts, the code feature information can be used to make the predictions, maybe across problems share similar skills. However, when you compare with the problem 236, you can see like this is the only question asking 3-way interactive comparisons. And then this doesn't work for Code-DKT because it only has the input from this single problem that has the code structure like that. And this is very different from the other problems submissions. So now we know that code features are indicative of students' next problem success across problems only when they share similar skills. This also makes sense, right? Some discussions here. First question, why DKT doesn't have a high performance? Maybe it is because that CS education is pretty hard. It's like complex. Students may make it incorrect because of different reasons, like students don't know if, students don't know how to use the variables. And also it is maybe because that it is a small data set. And the question 2, how code features improve the knowledge tracing models? We can say simple extensions just does not work, right? Like the TF-IDF or the expert features. And the structural information specifically extracted by the Code-DKT that helped. Question 3, when and how these features work. We can say when the problems share similar learning concepts, such as like the 5 of the 6 problems did well. And also when we want to make the predictions on whether students change the problem they attempt, then Code-DKT performs way better than DKT. Because DKT doesn't have information like what code students previously have submitted. Some limitations of this work. So we have a relatively low performance still, like 70, 80, something like that. So because it is a hard problem and we only have a limited single semester information here, right? And DKT is just a relatively simple baseline to compare with as well. And we also used a very simple like code-to-vec structure to show that, well, this probably will work. However, for future work, maybe we can do something like we use more advanced embeddings. How about like try to incorporate codecs things into this, right? Like GPT-3 pre-trained in the educational model, right? Educational data sets. We can also do the knowledge and skill attribution where like we can see what exact skills students don't know, such as like, well, in the next submission, students will fail, but on what skill? On the if skill, or on the variable skill, right? And also finally, we want to make some deployment and do some evaluations on the real classroom settings. And that concludes my presentation. Thank you.